Hi, my name is Patrick Bounds, and this is my ITCS 5156 final project. It is predicting powerlifting performance with machine learning. Recently, powerlifting has become one of the world's most popular sports, with competitors doing mind-blowing feats of strength like pulling planes or deadlifting thousands of pounds. But there's still a largely unexplored field from data scientists and lots of pseudoscience that surrounds what makes a great lifter and what wins events. So this project seeks to explore some of that by using a powerlifting competition dataset to better understand what makes the great aspects of a competitor. And we're going to try to do this by seeing if we can make a model that predicts competitor performance. Looking at the dataset, during a powerlifting competition, the lifter is classed based on their age, sex, weight, etc. The lifter then has 4 attempts to lift the most weight possible in the deadlift, bench press, and squat. At the end of the competition, the competitor who has the highest total weight between those 3 lifts wins the class. I downloaded this data set from the Open Powerlifting organization that keeps up-to-date records from events from around the world. So some previous work that's done in data sets like this is from Chong et al., who attempted a similar work with housing prices in Beijing. They used random forest, XGBoost, and light gradient machine boosting, all regression methods that did fairly well on predicting housing prices with the high 90% accuracies. Ping Feng used novel neural networks to actually predict the best individual lift, bench press, squat, and deadlift from male powerlifters, but this novel approach would have been too hard to implement in this paper. Gosaker and DeHang tried to estimate real estate prices in India using simple linear regression methods, and while this work didn't have great accuracy, it did show that there was some merit in attempting to use simple linear models as first estimates. So the methods I decided to apply was to mimic Chong et al., use decision tree, random forest, and extreme gradient boosting. In addition to this, some of the methods that we learned in class that I also applied as precursors were lasso regression and ridge regression. Each of these models were implemented using scikit-learn and Conda. This allowed for an easy implementation, and it allowed for low troubleshooting because all the models were validated before they were ever put into scikit-learn, so this saved time versus using a more novel approach. The method then involved tuning the hyperparameters for each one of these models. I first did this by mimicking the values of Chong et al. And making a baseline using a 5-fold cross-validation technique implemented in scikit-learn. The key parameter of the model was then swept through manually, much like in a grid search technique. This was done by writing a wrapper around the scikit-learn functions and allowed for easy training and evaluation with one function call. It would generate a plot, as seen here on the bottom, which would allow to see overfitting, as seen here, and pick out the optimal parameter for the hyperparameter. The dataset originally started out with 1.8 million entries and 22 features. I cleared out all of the NaN values, and any non-useful information such as the name or where the event was held was stripped. A new feature was created for each lift that told if the lifter failed any of their individual attempts, and all the individual attempts were thrown out themselves except for the best lift that was succeeded. Finally, lifter equipment was one-hot encoded, and the final dataset ended with 1.6 million entries and 13 features. Of the 13 features, only 2 of them were continuous, age and body weight, and the rest of the features were Boolean, which we'll touch on in a minute. Looking at the correlation heat map, we see this is the total kilogram, which we are trying to predict, and these are all the correlations. You'll notice 3 features, the best squat, best bench, and best deadlift. These simply make a linear combination to get total kilograms, and that's why they are heavily correlated. So the first results we used, we validated with a 5-fold approach, and one of the things that I can see here is that none of these methods have acceptable accuracy. They're all below the 55% mark, and they all perform about the same, with XGBoost or random forest being the best, and the 2 linear regression methods being the worst. So why did these models perform well for Chong et al. And not? Well, this brings us to our problem challenges. The first challenge was I thought this might be hyperparameter tuning. So I followed the hyperparameter method more. I did more grid searches on key parameters, trying to find the best parameter at every step, but this still didn't really result in anything. It was very computationally expensive. I was only gaining accuracies of increases about 2 or 3%. So the second more pressing challenge is, why were these initial results kind of all the same and not receiving accuracies even in the range of what Trong et al. Did? Since it wasn't the hyperparameters, what could it be? After looking at the data set more and getting some advice from our TA Ben, he said that it might just be that the data set does not contain enough feature richness to be able to really make a good prediction, considering that most of the variables were Boolean and only 2 of them were continuous. These models' complexities might not be good enough to capture a good prediction without these. So we shifted how we explored it a little bit, and then I changed to doing 3 individual regression problems with a new individual lift introduced at each stage. So what this would mimic is a competitor could put in all of their attributes and then what their best lift on, say, bench press would be, and this model will make a prediction at what their total for an event would be. So when we include the bench press, we do see that the accuracy goes up across the board, but it's not a significant increase. It's still below what we would want to see. We then use the squat, and we actually see that the scores increase tremendously, with it being in the mid-90s in accuracy, with XGBoost and Random Forest the best. We then look and we see that when we include the deadlift, the accuracies go up, but not as much as when we include the squat. Looking at a summary of all these, you can clearly see that the squat is the best feature predictor, followed by deadlift, followed by bench press. The interesting thing about this is that the squat is not the lift that has the highest mean weight. That is actually the deadlift. And being that these were a linear combination, I came in with the assumption that the best predictor would be the one that contributes most to the total. But in fact, squat contributes the least amount to the total, as it has the lowest average out of bench and deadlift and the squat, those 3 respectively. The other thing we see is that XGBoost and Random Forest are the best models across the board for any combination of the features. So looking at some of the conclusions from this work, the powerlifting dataset did not contain sufficient data for the applied models to predict a total score with at least one subscore as a feature. So it needed one of the lifts to be able to predict accurately. Of the models applied, XGBoost did the best at predicting performance across all feature set combinations, and this was followed by Random Forest. When including the individual lifts as features, the squat was seen to be the best predictor, followed by the deadlift. For some of the future work, some of the methods that I would like to apply would be working with more complex models like neural networks to see if they can achieve better performance without including sublifts. Apply feature engineering to create new features out of some of the unused or useless features, like categorizing where a lifter places in their age class. And finally, explore model explainability techniques and the dataset to try to better understand why squatting was the best predicting feature. Thank you for looking at my project, and I look forward to seeing all others. Here are a few of my references.